What makes a bicycle stable using control theory? Imagine riding a bicycle on a windy day. You might feel it wobble or sway, but at higher speeds, it often feels surprisingly steady. How does that happen? Let's explore how control theory explains bicycle stability. Bicycle stability can be viewed as a dynamic system with feedback loops that keep it upright. Think of the bicycle as an inverted pendulum, which naturally wants to fall over. Without intervention, it's unstable. But the rider and the bike's design work together to create stability through feedback. When the bike leans to one side, the front wheel automatically turns into the lean. This steering action produces a torque that pushes the bike back upright, acting like a natural correction. The geometry of the bike plays a big role here. The angle of the front fork and the trail, which is the horizontal distance between where the wheel touches the ground and the steering axis, help the bike steer into the lean. This mechanical feedback is passive, meaning it happens naturally without any rider input. It's like the bike's built-in stabilizer. Speed is another key factor. When you go faster, the spinning wheels generate gyroscopic effects. These gyroscopic moments resist changes in lean, helping the bike stay upright. There's a certain speed called the critical velocity. Above this speed, the combined effect of the trail and gyroscopic forces makes the bike self-stabilizing. Below that speed, the rider has to actively steer to keep balance. Mathematically, the lean angle and steer angle can be described with differential equations. These equations show how the angles influence each other over time. If the feedback control is tuned correctly, the system becomes stable. For example, if the steer angle adjusts proportionally to the lean angle, the bike can correct itself dynamically. This is similar to how control systems in electrical engineering work. Gyroscopic effects from the spinning wheels add to this stability. They resist rapid changes in lean, especially at higher speeds. This velocity-dependent effect makes the bike more stable without rider effort. From a control system's perspective, the bicycle is like a feedback loop. The lean angle is the output we want to control, and the steer angle is the input we can adjust. The forward speed influences how the system responds. When the system's poles and zeros are in the right places, the bicycle remains upright. If the parameters shift, stability can be lost, and the bike might fall. Practically, this means that at high speeds, the bike's design and gyroscopic effects do most of the work. You can even ride hands-free if you're going fast enough. But at low speeds, you need to actively steer and balance. Bicycle designers optimize parameters like wheelbase, fork angle, and trail to find a good balance between stability and maneuverability. In summary, a bicycle stays stable because of a mix of mechanical design that provides passive feedback, gyroscopic effects from the spinning wheels, and rider input. Control theory models this as a feedback system where the lean angle is regulated by steering torque. Stability depends on speed and geometry, making the bicycle a fascinating example of a real-world control system in action.